You've probably seen this bridge before, maybe from afar, maybe while driving, maybe in photos of Johannesburg, and at first glance, it just looks like a normal bridge. But the more you look at it, the stranger it becomes, because this bridge crosses over more than 40 railway lines below it, and yet when you look underneath, you do not see a bunch of supports holding it up. It is one of the biggest cable-stayed bridges in southern Africa, stretching about 295 meters across the rail yards between Braamfontein and Newtown. Most people think bridges work in one simple way. You build the road, then you put columns underneath it. Then the columns carry the load to the ground. Simple. That's the bridge logic most people have in their heads. But this bridge does not behave the way most people expect. And that is exactly why it's so fascinating. Imagine you have a long plank. If you try to support it from below, you put columns underneath. That's how most bridges work. But now imagine something different. Instead of pushing the plank up from below, you take ropes and you pull it up from above. That's exactly what's happening here. The road you're driving on is being held up from the top. Those cables are connected to the bridge deck and they run up into those tall towers. And when the weight of cars pushes down on the bridge, the cables go into tension. They stretch slightly and they pull that load upward into the towers. So now the load path looks like this. Cars push down, the bridge deck carries that load. The cables pull it upward. The towers receive that force and then send it into the ground. So instead of the bridge being supported from below, it is being held up from above. And once you see that, you start to realize something. This bridge is not just sitting there. It is being actively held in place by forces you can't see. Now, here's something else that's interesting. The Mandela Bridge doesn't look like this just because it's modern. It looks like this because of what's underneath it. Below this bridge are railway lines, a lot of them, dozens. And those trains don't stop just because you want to build a bridge. You can't just go and put columns or supports anywhere you feel like it, because the moment you do that, you block the trains. So now engineers have a problem, not a small one, a very specific big one. How do you build a bridge across this entire space without putting anything in the way below? That constraint changes everything. You can't support the bridge from the ground underneath, so you have to find another way. And that's why this bridge is supported from above. Those towers and cables are not just a design choice, they are a solution to the fact that the space below had to stay completely open. And once you realize that, the whole bridge starts to make sense. It's not just a structure, it's a response to a very real problem. Now, here's something most people don't think about at all. Those cables above you are not just holding up the Mandela Bridge. They are being pulled extremely tight, not slightly, extremely tight, because they are carrying the weight of the entire bridge and everything on it. Now, think about a rubber band. If you pull it tight between your fingers, you can feel that force, and if it snaps, it stings. That's because all that stored energy is released instantly. Now, imagine that same idea, but on a completely different scale. These cables are like very powerful versions of that rubber band. They are constantly being pulled to keep the bridge exactly where it needs to be. And right now, as you're driving or walking across the bridge, that force is there, holding everything in place. Now, here's the important part. In real engineering, you don't just assume everything will always stay perfect. So the bridge is not designed with just enough cables. It's designed so that if one cable fails, the others can still take over, because the moment one cable is gone, that force doesn't disappear, it shifts, and the structure has to be ready for that. So what you're looking at is not just a bridge, it's a system that's been designed to handle extreme forces and still stay standing. Now, here's something most people don't realize. This type of bridge is not just visually different. It's one of the most efficient ways to build a bridge, because instead of using a lot of material underneath like columns and supports in heavy structures, this design uses cables to do most of the work, which means you can span a large distance using less material and you can still carry massive loads. And that's why you see this type of bridge in cities all over the world. Not because it looks good, but because it makes sense. It solves a very specific problem. How do you cross a large space without blocking what's below and without building something unnecessarily heavy? And this is the answer. So what you're looking at here is not just a bridge in Johannesburg. It's a very specific engineering solution to a very specific problem used all over the world for exactly this kind of challenge. Hi everyone, the South African engineer here. If this explanation was useful, please like the video, subscribe, and turn on your notifications. Every subscription is a brick used to build the Engineering Explained house. Let's build this house together. Thank you for watching.